Problem 14. In problem 14, I have a geology map which shows the trace of the fault and the attitude of the dike, and strike separation is 450 meters, or the offset of the fault, and I'm supposed to calculate the amount of slip, okay, for two different settings. One, if I assume the fault is a pure normal fault and has no oblique movement, and the second time I should assume the fault is an oblique movement and the pitch or the rake of the slicken line is 60 degrees. So before going in details, let me give you a little bit of information about this map. Okay, let's say this is the dike and the fault is going through with this orientation. As you notice, the dip of the dike is 90 degrees, and I will apply the strike slip movement along the fault trace, and as you see, you're gonna have an offset in the map view. Either you apply the left lateral or right lateral movement along the fault trace. So let's see how it looks like in the normal and reverse fault. Now this time this is my footwall, this is the fault plane, okay, sitting here, and this one is the hanging wall. I'm just gonna apply the pure normal movement. It means the rake of the movement is 90 degrees. There is no oblique movement. And let's see what will happen with the trace of the dike in the map view. If I move the hanging wall, okay, you wouldn't see any offset in the map view. The same thing, if this is this is a footwall, this is the fault, and this is the hanging wall, and this time I'm gonna apply the reverse movement, okay, or I'm gonna demonstrate the reverse fault. So if I move the hanging wall towards upside, okay, so you wouldn't expect any offset along the fault trace. So things get complicated when the dike or bedding has a dip less than 90 degrees. So let's say this time this is the dip of this is the dike and is dipping towards me, and I have a fault trace going like that, or the fault orientation is like this, and I'm gonna apply first a strike slip movement. Okay, the offset is there, it's normal. I expect having this much of offset. But what about the normal fault and reverse fault? Let's say this time this is my hanging wall and the fault is sitting like that, okay, and this block is the footwall. So I'm just gonna move the hanging wall with 90 degrees rake along the fault plane, okay, on the deep direction of the fault. If I apply that, okay, you're gonna see the offset in the map view, right? I'm talking about these lines, okay? If this is normal fault, I'm just moving downside, but you still will see the offset in the map view. So even though there is no oblique movement, okay, there is no oblique movement, I'm just moving down. Or again, the same thing, if it's a reverse fault and I'm just moving this block up, okay, you're gonna see some kind of offset in the map view. So of course, if we have the oblique movement, the offset is you're gonna expect the offset. But the point is, okay, the point of this demonstration is if the bedding or a dike is dipping less than 90 degrees and the movement along the fault is just normal fault or reverse fault with a rake of 90 degrees, you can still see the offset. And seeing offset in the map view, it doesn't mean you have a oblique movement. So that's why in this question, okay, it says assume this is the normal fault, or assumed it's the oblique fault, and for each example calculate the net slip. So I'm gonna start working on this question, and I will show you how you can calculate the net slip along the fault plane. Okay, let's start by plotting attitude of the fault and the dike on the stereo net. The strike of the fault is 330. Okay, this is 360, 350, 340, 330. This is the fault and is dipping towards southwest. It's dipping to that direction, 50 degrees. 10, 20, 30, 40, 50. Okay, this is the fault. The dike is 40 degrees. Okay, the azimuth of the strike is 40. 10, 20, 30, 40. And is dipping towards southeast, 35 degrees. Ten, 20, 30, and 35. Okay, let me see what else I have on the question that would help me. On the stereo net, nothing. This is all. So what you can extract from this stereo net is indeed we have the intersection point, okay, is here. Okay, I have the intersection point. I'm gonna count the angle along the fault plane. What you do, you rotate your tracing paper and place it the fault strike along the north-south, and then you count the degree along the fault trace. So 10, 20, 30, 35. You write the 35 degrees over there. So what that means, let's demonstrate the fault and also dike in 3D space, and then I can show you what this angle means. Let's say this is my fault, the orientation of the fault and the dip, and this is the dike is oriented like that. Okay, it's dipping this much, and indeed this is what we plotted on the stereo net. The 35 degrees indeed is this angle. Okay, is the angle between the fault strike and the trace of the dike on the fault plane. Okay, because I'm going to calculate the net slip, which is the displacement along this plane. That's why I need an angle of this on this plane. So the only angle up to now based on this information I can calculate indeed is the angle between the strike of the fault and the trace of the dike on the fault plane. Okay, I have this 35 on the fault plane, and I can use this one as one of the angles to find out the slip movement on the fault plane. Okay, I replaced 35 degrees with 34 degrees. Why I'm doing this? Because I don't want to get confused between this angle, the dip of the dike, and this one. Okay, let's take this one as a 34. So next step, you move to the map view, and you trace the you trace the footwall. Okay, this is the footwall, this is the hanging wall. I will trace all the information on a piece of vellum paper, and let me show you here. This is the fault plane, okay, and this is the trace of the bedding on the footwall. Okay, I'm not gonna drop both of them. Okay, just choose the bottom side or the top side for both of them. Okay, and go with only one line, which will make much more easier for your calculation. Okay, this is the trace of the bottom side of the bedding. Okay, and I'm gonna just put a sign on the bottom side of the dike or the bedding along the fault trace using the outcrop in the hanging wall. Okay, so this one is 450 meters. Okay, so if you remember, this is all we need from this map. So if you remember, we had this angle, right? So I fold my vellum paper. Okay, this is the map view, and this is the fault plane. Okay, and there is an angle that I measured here. If I write anything here or show any angle here and unfold this, it's not gonna change. Okay, so let's do that. Let me first here I show you the angle, the 34 degrees angle from this point. So I will take 34 degrees. Okay, this is the trace of the dike. Let me bring my dike. Okay, this is the trace of the dike on the fault plane. Okay, with the strike of the fault, 34 degrees. So you can unfold this. Okay, it's not gonna change anything, and you write down 40 degrees here. Okay, okay, so far I have the trace of the dike on the fault plane with an angle of 34. I have the offset in the map view, and I am going to calculate the slip movement if the fault is pure normal fault. Okay, which means the dike, okay, in the hanging wall, okay, it's just moved from there to here. How much actually the footwall moved down along the fault plane. So I know if the fault is normal fault and there is no oblique sense, then the rake should be 90 degrees, right? So in that case, I take my ruler and I place it along the fault plane here, and I will draw a vertical line to the fault trace, and this is gonna be the maximum or the total slip movement if the rake is 90 degrees. Okay, so I need this one, X, and indeed how you can find the X, I know this is 90 degrees, and yet you can write down tangent of 34 degrees is equal opposite or adjacent, right? X over 450 meters. So the X is equal 450 meters multiplied by tangent 34 degrees. Okay, tangent 34 is 0.6745. Let's multiply these two. Multiply 40. Okay, it's gonna be 303 meters, 0.5 meters. Okay, if the fault is normal with no oblique movement. Okay, the second portion of the question, it asks how much is the slip movement if the rake of the fault is 60 degrees. What we calculated here, it was for the rake of 90 degrees, which is the pure normal fault. If we are supposed to calculate for 60 degrees, what you do, you find the 60 degrees here. This is my 60 degrees. Okay, now I have a new triangle, and I'm interested to sigma prime this time. Okay, so I think it's clear, but let me highlight the triangle that this time I will use with the dash line. I'm using this triangle. Okay, so this time this angle, it should be 60 degrees, right? This is 60. Let's highlight it. This is 60 degrees. This is 34 degrees. And this time this has to be, we can calculate 180 minus 60 minus 34. It's gonna be 86 degrees. Okay, it's not 90, it's 86 degrees. Okay, I have now this triangle. What I did, I just took the note. Okay, so here it's 450 meters, this side of the triangle, and triangles are noun, right? 34 degrees, 60 degrees, and 86 degrees. So you cannot use the tangent like the one that we used before. This time I'm interested to this one, right? Let's say x prime. And how I should find this, I can write sine 34 degrees over x prime is equal sine 86 degrees over 450 meters. Okay, so the x prime is equal 450 meters multiplied by sine 34 divided by sine 86 equal 400 meters multiplied by 0.559, and the sine of 86 degrees is 0.997. If you do this multiplication, it's gonna be x prime is equal 252.3 meters. Okay, this is the slip movement of the of the oblique fault with a rake of 60 degrees. And you are done.